So this was the first question that kind of a lot of people seem to ask me about. And so I made up one that was similar, but a little bit different. Stop doing that. This thing's not on. All right. So this is kind of like the one that was asked. I don't remember exactly what the context was, but here is a situation. The average temp by month is a sinusoidal function. And all this word means is just that it's either sine or cosine. Right? Sinusoidal is a fancy word for saying sine or cosine. With a low value of 30 degrees in January and a high value of 110 degrees in July. What's the function? And so we're making the same assumptions that were made in the homework problem that was given, that time is measured in months, time is equal to 0 is January 1st, and time equal to 6 is July 1st. So we can draw the graph without too much trouble. I think I can do it down here. So the idea is we're hitting a low value of 30 at the very beginning at time equals 0. So here's our low value of 30 degrees, temperature degrees, for not angle degrees. And then up here, we know we're going to hit a high of 110 halfway through the year. So right, here's time equals 6. Here's time equals 12. Here's time equals 0. So what's happening is we're starting here, and then halfway through we're reaching a peak. And at the end of the year, we're going to be back to 0. And so what this is going to look like is it's going to keep doing that same sort of thing. And so our job is to kind of identify the few kind of things about this trig function that we need, namely the amplitude, the vertical shift, and the period. And then if there's any kind of like reflection. And I did this differently than some other people wanted to do, but I think the other way was probably better. So I think it's nice to see this as it looks like a cosine function, but flipped over. Of course, we don't have all the room in the world, so I think I can erase. Yeah, I can erase this. We've got all the important stuff here. Sorry, we're trying to determine what trig function this is. We've got a period of 12. We've got our amplitude. What is our amplitude? Well, we're going from 30 to 110, so we have a range of 80 degrees. Our amplitude is going to be half that range. Right? If you think about like a regular sine function or cosine function, the amplitude is usually 1. It has a range of +1 down to -1, so it's got a range that's a length of 2. So here our amplitude is just half whatever the length of the range is. So our amplitude is going to be 110 minus 30 is 80, so half of that is 40. So we're looking at something kind of like this. We've got 40 cosine of something. The problem with this is a couple things. And 40 cosine 1, it's not going to start down low, it's going to start up high. So it would look like this. Now let's just say 40 cosine of x for a moment. Here's what 40 cosine of x would look like. So that's got two problems really. One, I need to flip it over. So I need a negative. That's going to flip it over. And my drawing's not great, sorry. And then the other thing I need to do is I need to shift it up, right? I want the low point to be at 30, not at -40. Oh, I just made this problem up, Allie. It's similar to a homework problem, but it's not quite the same. A lot of the problems we do, I will just make up. So let me ask you guys, what do I need to do to this equation to shift this up so that the bottom is, instead of being -40, is at +30? Or even better, what do I need to add to the function so that instead of being negative 40, the bottom is a positive 30? Exactly. I'm going to add 70. So this here, well, actually, I'll say, if I do that, I'm getting close. In fact, I'm really close. The only thing is that my period isn't quite right. Right, this is going to look like this, but the normal period for a trig function is 2 pi. Now, that's definitely not what we want here, right? We don't want 2 pi months, or about 6.2 months. We want 12 months. So how do we change our period? Well, in general, if you have y equal to sine of x or cosine of x, I just say sine of b times x or cosine of b times x. I don't know why we usually use b here, but we do. The period is equal to 2 pi divided by b. So if I want the period to equal 12, then I can set 2 pi divided by b to be equal to 12 and then solve for b. So multiplying both sides by b, I get 2 pi equal to b. 2 pi equal to 12 times b. And then dividing both sides by 12, I get 2 pi divided by 12 equal to b. Or reducing that fraction, pi divided by 6 equal to b. So what I actually need to get this graph down here is negative 40 cosine of pi over 6 times x plus 70. That'll give me this sinusoidal function that has a low at the beginning of the year of 30 degrees, a high in the middle at 6, a low at the end at 12. And we could even check values if we really wanted to. Right? If you plug in 0, you'll get negative 40 times cosine of 0, and cosine of 0 is 1. Sorry, you can't see my finger. Cosine of 0 is 1. And then plus 70 would give you 30. And then in the middle, at time equals 6, if you plug in 6, pi over 6 times 6 is pi. Cosine of pi is negative 1. Negative 40 times negative 1 is positive 40. Plus 70 gives you 110. So we can see that, oh yeah, at 0 we're getting 30. At 6 we're getting 110. This seems to be the right function. And then if you really wanted to, you could take the thing you've got and you could go graph it on Desmos and see if it actually looks like the thing you think it's supposed to look like. That's what I would probably do. So there are questions about this. Oh, I do see someone. No, yeah, you're good, Ali. So I'm not sure if it's Ali or Ali. I apologize if I say your name wrong, but I will always do my best. Excuse me. So, questions about this problem?
I have a question. So it's negative 40, right? And it's negative because we flipped it?
Correct. Now, I will mention this isn't the only answer. There are other ways you could write the answer. Specifically, instead of doing negative 40 cosine, you could, in fact, this is a great time. I'm going to show you guys on Desmos because I think it's easier than me trying to draw. So you could do, grab my share. Let me get faster at this one of these days. That's not what I wanted. There we go. So we can totally graph this, right? Y equals to negative 40 cosine of pi over 6x plus 100 plus 70. Can't obviously see it because we're not in the right range, so let's zoom out a little bit. So there we go. We can see the function. Definitely starts at a low of 30, hits a high of 110, goes back to a low of 30 when we're getting to 12, right? Because there's 10, so there's 12. So it looks right. We also could have done it this way. Y equal to, let's see. I'm gonna guess. It's probably gonna be wrong. Let's try 40 sine of pi over 6 x plus 70. So if you look at that, it looks mostly right, except it's shifted a little bit to the left of where I want it. In fact, it seems to be shifted, looks like 3 to the left. So I want to shift it back 3 to the right. What I can do is I can take that x, and instead of just having x, I can put parentheses around it and have x minus 3. And I'll shift it 3 to the right to get the same function. And so what's really kind of true is sine and cosine are really the same function. They're just the same function shifted either to the left or to the right. So there are definitely many ways you could write this. And then you could also, if you really want to, you could distribute the pi over 6. You could also write it like this, where you get pi over 6 times x, and then pi over 6 times 3 is just pi over 2. So there's a third, right? But that's just kind of distributing the pi over 6 there. So all these 3 ways of writing this graph give you the same function or give you the same graph, but there are slightly different ways of writing it. So yeah, sine and cosine are just horizontally shifted versions of each other. Yeah, that's it. Other questions about this? The other side is erased. Let's see, what else? Another thing people I noticed had a lot of questions on were the domain of composite functions. Really, domain in general and domain of composite functions between that. No, you ask. I think you still want 12 for that problem melody. I know it's kind of weird with time, but I think, yeah, I'm pretty sure you want it to be 12 still. I know t equals 1 is January 1st. So I mean t equals 0 is January 1st. And then they say t equals 6 is July 1st. So that means t equals 11 would be December 1st. But then t equals 12 would be the end of the period and would be the next January 1st. Hopefully that clears that up. Yeah, it's always weird when you've got time and you've got dates. It can get a little bit confusing. Usually things work the way you would expect them to. You don't have to you don't usually have to adjust for being off by 1, but it can be strange. So I saw some of you had some kind of strange domain questions. So we'll kind of look at those first, and then I'll show you some more normal questions. So let's look at the following. Try my blue pens. I need to start throwing away pens. I'll just use green. Let's see how. Tell me if the green looks okay. So I turned off some settings, so it should look all right. So we've got this function, f of x equal to the square root of x plus 2. I don't know about that. Let's take a look. Sorry, I didn't mean to do that. That's interesting. I keep turning off the adjusting for low light and it keeps coming back on. I don't know why. I don't want you to be automatically on. Hopefully you can see that a little bit better now. So here's my function, square root of x plus 2. And I'm going to say that the domain is x is bigger than or equal to 7. Which is kind of a weird thing to say, right? That's not the usual domain. But we have just decided that for this function, that's going to be the domain. And then for g of x equal to x squared plus 5. And here we're going to say the domain is that x is greater than or equal to 4. So these are what are usually called oh my gosh, the words. The words are escaping me. Sorry. We call this a explicit domain. Sorry. So like if you look at this function, normally you would kind of talk about the implicit domain, meaning what are all the things x is just allowed to be or not allowed to be, which would be x plus 2 would have to be greater than or equal to 0. So here the implicit domain would be that x plus 2 is greater than or equal to 0, or x is greater than or equal to negative 2. But sometimes we just want to say, well, for some good reason, it makes sense to say that the domain is what we want it to be. Maybe this is your function, you're starting 7 days into the week, or something strange like that. It feels very artificial, but it's fine. So then we want to look at the domain of the composition. We're going to look at both f of g and g of f. So let's first look at f of g of x. And the thing I want to emphasize about the domain of a composition of functions is you always have to obey the domain of the inner function. Then there might also be some other stuff we have to look at, but for sure, since g of x is the inside function, we're going to have the x is bigger than or equal to 4. No doubt. We might also have other restrictions, but definitely that one. So I've got f of g, which is x squared plus 5. And then that's going to be f of x squared plus 5 is going to be the square root of, instead of x plus 2, it'll be x squared plus 5 plus 2, which we could simplify as the square root of x squared plus 7. Okay, so we have to check that the domain of the inner function and the outer function are both kind of satisfied here. So first off, we definitely need, for here, since we've got x squared plus 5 as our inner function, we have to have that x is greater than or equal to 4. Because the inner function isn't really kind of being modified in any way. So then, the other thing we have to check, and I know it seems kind of strange, is that, so the thing that we're putting into f, right? F has a domain where the input has to be bigger than or equal to 7. So let me ask you guys, is this bigger than or equal to 7? Well, not always, right? X could be 0, and 0 squared plus 5 isn't bigger than or equal to 7. So let me ask the follow-up question then. Is this always bigger than or equal to 7 if x is bigger than or equal to 4? Oh yeah, it is, right? If x is bigger than or equal to 4, this is 4 squared plus 5, it's 21. So this part is okay, right? This is satisfied because the domain of the inside function is already kind of taking care of it. So here, we would say that f of g of x is the square root of x squared plus 7, and the domain would be that x is bigger than or equal to 4. And although I'm writing it this way, the way we probably typically want to write this is using the interval notation, where we're going to say, okay, I want everything starting at 4 inclusive with a bracket, and then going to infinity. So that's the domain of that function, everything from 4 to infinity.
I have a question.
Yeah.
Why wouldn't you solve for x squared plus 5 is greater than or equal to 7?
That's a good question. I guess we could. I guess I didn't think about doing it that way. If we did that, so x squared plus 5 greater than or equal to 7, x squared greater than or equal to 2, x greater than or equal to the square root of 2. Technically, x is greater than or equal to the square root of 2, or x is less than or equal to the negative square root of 2. So that's actually a perfectly good idea. I think the reason I didn't do that was because I saw that we were already going to kind of satisfy what we needed. So here's the thing. We're getting this condition, but we also have to meet this condition. So here's what this is looking like. So we have to be bigger than or equal to 4. And then this other condition here says x could be bigger than or equal to root 2. So all this, or x could be less than or equal to negative root 2. So we have to have this be true for sure and that be true. So for them both to be true, we have to have where they overlap, or intersect is the more mathematical word, which is right here. This is the place where x is bigger than or equal to 4 and x is bigger than or equal to root 2, or x is less than or equal to negative root 2. So we're just still stuck with x being bigger than or equal to 4. It's kind of weird, I know. Does that clarify what's going on?
Yeah, I get it now. Thank you.
How did you get the x is greater than or equal to negative, or the square root of 2?
Sure. So from x squared bigger than or equal to 2, there's a, so what I really did was, so I don't understand this actually. So what I did there, there's a couple ways to attack it. What I really did was I took the square root of both sides. So I said the square root of x squared is bigger than or equal to the square root of 2. And now here's kind of a tricky thing that I think we might have said last class, but I don't remember exactly. What's the square root of x squared?
Absolute value of x.
Exactly. So if the absolute value of x is bigger than or equal to 2, that means either the insides have to be bigger than or equal to root 2. Right, so like if x is 3, the absolute value of 3 is definitely bigger than the square root of 2. But it could also mean that x is less than or equal to the negative of the square root, or the negative of this, right? If x is negative 3, the absolute value of negative 3 is still 3, which is still bigger than or equal to the square root of 2. So that's kind of the work that I did. Although there are other ways you could solve it.
What would be like the preferred answer?
To the question of what the domain is?
Yeah.
So the answer for the domain is still just this part here. Because even though we were talking about this, because so the reason we got to here was we said, oh yeah, this part here, this x squared plus 5, we need the input of the f of x function, or the f of g of x function. We need that input to be bigger than or equal to 7, because we have artificially said that the domain there is bigger than or equal to 7. So someone pointed out that it made sense to say, well, let's just set that stuff to be bigger than or equal to 7. We did that, we got this. And then we said, well, we have to have this being true, that x is bigger than or equal to 4, and this being true. And so for them both to be true, you have to have where they overlap, which is, I know I'm running out of room here. I might just erase this. So bigger than or equal to 4 is right here. And then in a different color, here's bigger than or equal to root 2. And here's less than or equal to negative root 2. But the problem is the only place where these overlap is here. So that's what the domain is. So let's talk about the other direction. Let's do, or the other composition. Let's do g of f of x and see what happens. G of f of x is g of square root of x plus 2. Remembering here that x has to be bigger than or equal to 7. And then g was the function x squared plus 5. So it's my stuff squared plus 5. And so we can totally simplify this, right? Square root of x plus 2 squared is just x plus 2 plus 5, which is x plus 7. So our function is just g of f of x is equal to x plus 7. But like was pointed out before, we still need So remember, g of f of x, or I should say g of x, the domain for g of x equal to x squared plus 5 was x greater than or equal to 4. So we need the input to be greater than or equal to 4. And I think exactly what, I don't know who said it last time, but we should just say that this stuff here needs to be greater than or equal to 4. And we can solve that. We can square both sides. And we can subtract 2 from both sides. So even though the inner function needs x to be bigger than or equal to 7, the overall composition, we also need x to be bigger than or equal to 14. So if we look at where those two things overlap, right, here's x bigger than or equal to 7. Here's x bigger than or equal to 14. And since we have to satisfy both conditions, we only get the overlapping parts where x is bigger than or equal to 14. So the domain for this composition, f of g of x equal to x plus 7, that has a domain that is x bigger than or equal to 14, which we would probably preferably write as 14 comma infinity, with a bracket on the 14 to include the 14 and a parentheses always on the infinities. So questions about this one before I show you a more normal one.
So whenever we're doing these type of problems, we're always gonna have to be looking where the domains are basically like not intersecting, but you know where they're
using the right word. Intersecting is the correct word.
Oh, okay.
Yeah, that is. I can't think of a case where that's not true. So yes, I believe that is correct.
I have a question.
Yeah.
So what if they ask you for the range? How would you find that?
So the range is more challenging. Typically, we have kind of two methods at our disposal, and it really, really depends. Sometimes, although I don't think it's for any of these problems, sometimes you can find the range by finding the inverse function and then finding the domain of the inverse function. It doesn't really apply here, but that is one method that is sometimes available to you. Other than that, the way we typically find the range is graphically. So we could totally graph this. It's actually not hard to graph. I'm going to erase this there. This one is especially probably the easier of the two examples. So I can graph g of f of x equal to x plus 7. And I know my domain is starting at 14. So if I start over here at x equal to 14, I know that if I plug in 14, right, if I'm essentially graphing y equals 14 plus 7, sorry, not 14 plus 7, y equals x plus 7, then if I plug in 14, 14 plus 7 is 21. So that's kind of my starting point. And then it just looks like this. So that's what the graph of that looks like, right? It looks like y equals x plus 7, but it's been cut off so that I only get everything to the right of 14. And so the range here is all the y values. So the range is starting at a low of 21 and going up and up and up and up and up. So that's what the range would look like here. Sometimes, like in this example, it is much easier than other times. This one was super straightforward to graph. Let's take a look at the flip side to see if it's more challenging.
I have a question.
Yeah, go ahead.
Oh, sorry. After you're done, could you please explain how you got the domain for the second one again? Because I'm still a little confused on it.
Oh, sure. No, we can take a look at it real quick. So,
Okay.
the way we got the domain here was we said that both x had to be bigger than or equal to 7, but we also said that the input for the g function, right? So what's going in here, right? G of x said that the domain was the x's, or the inputs had to be bigger than or equal to 4. So we said, oh, this input, square root of x plus 2, that thing that we're putting into g, that had to be bigger than or equal to 4. And that's how we found the domain here, was by solving this inequality. We squared both sides, and then we subtracted 2.
Why wouldn't it be x? Wouldn't it be greater or equal to 7?
Well, that is also a condition, but being bigger than or equal to 14 is the more restrictive condition. So, right, being bigger than or equal to 14, it is also true that we are bigger than or equal to 7. So this is where we're getting the intersection of those two things, right? Our domain here really is, I should have more room on this board. You're gonna hear me say that like a million times this quarter. So, right, so from the inner part, right, so the inner function has a domain that has x bigger than or equal to 7. That's from the f of x part. And then the outer thing, this is x bigger than or equal to 14, and that's from g of f of x, right? This is from really f of x having to be bigger than or equal to 4. And the thing is, when you compose functions, or really when you combine functions in any way, you have to obey the domains of like all the things. So it has to be true that we're obeying the domain of both the inner function and the outer function. So I have to obey this domain, and I have to obey this domain. And so since I have to obey this one, this is the more restrictive one, I can't be over here, right? If I pick a number like 8, I'm not allowed to pick a number like 8, right? If I plug in 8, well, great, sure, 8's bigger than 7, that's fine. But then the square root of 10, right? The square root of 10 isn't bigger than or equal to 4. So I'm not allowed to plug in a number 8 for x, because it'll mean I'm plugging in something that's too small for the domain of g. So that's why we have to pick just where they overlap. Going back to talking about the range, so we have this. I'm gonna erase some of this here. So what we ended up for this with this function was that g of, make sure I'm writing it right here. Yeah, this is f of g of x was equal to the square root of x squared plus 7, and our domain was x greater than or equal to 4. So this one actually isn't too terrible either. The way to make sure, let me think about that for a second. So graphing this, we would, so I'm just going to start at 4. If I plug in 4 squared is 16, 16 plus 7 is 23. Square root of 23 is a little bit less than 5. So I would probably do it like this. So here's my beginning point at 4 comma square root of 23. And then we are kind of lucky here in the example, because as x gets larger, the insides just keep getting larger and larger and larger. So as we pick values that are further to the right for x, the y values will get bigger. So this will do something like this, meaning it's going to keep growing larger and larger and larger. So the range here would be everything from the lowest y value of the square root of 23, and then the y values just keep getting larger and larger and larger. So to more generally answer the question about range, we're usually just looking at, most of the time we're trying to see, can we see what the graph tells us? Does it show us what our y values are? And in these two examples, it was relatively straightforward to just graph the thing and see, oh yeah, we've got a y value that's got some bottom and we just keep going up. That won't always be the case, but a lot of the time it will. And then someone asked the question, so how do we make sure we always use the most restricted domain? I don't have a good answer to that right off the top of my head. Let's look at, let's look at maybe let's look at a more natural example. Let's look at these two functions. Let's look at f of x equal to the square root of x plus 2 and g of x equal to the square root of 6 minus x. And before we compose these, I'm actually going to do something simpler. I'm just going to add them together. Actually, before I even do that, let's talk about the domains of each of them. So this function, the domain, and the way we find the domain of any kind of thing with a square root or an even root is by setting the insides to be greater than or equal to 0. Right? We don't take square roots of negative numbers in this class. We don't deal with any kind of imaginary stuff. I will point out that is definitely not true throughout the whole series. Once we get to 17C, I believe, we definitely talk about imaginary numbers. So we will be discussing square roots of negatives at some point during this 3 quarters of calculus. But for now, we're not. For now, they're off limits. So our domain here is x is bigger than or equal to -2 or -2 to infinity. Over here, same idea. The domain, we're going to set the insides 6 minus x to be greater than or equal to 0. So 6 is greater than or equal to x. Or you could read that as x is less than or equal to 6. So here the domain is everything from -infinity up to 6 equals 0. And so now I want to talk about what happens to the domain when we add these functions together. Right? If I just say like, what's f plus g of x, which is f of x plus g of x. Now I should point out, these are not artificial or explicit domains. These are the natural domains or the implicit domains, which is what kind of are more used to doing. So if I just look at the sum of these two functions, which is the square root of x plus 2 plus the square root of 6 minus x, I see here that I have to obey both domains, right? I have to have that x is less than or equal to -2. I also have to have that x, sorry, I said less than or equal to, I meant bigger than or equal to. I also have to have that x is less than or equal to 6. Because I need to meet both restrictions, right? If x was 7, 7 is fine here, right? Square root of 7 plus 2 is the square root of 9, which is 3. 7 is not okay here, right? I get a square root of a negative. And vice versa. If x is smaller than -2, like if x was, I don't know, -5 or negative, let's do -10. If x was -10, and -10 is perfectly okay here. 6 minus -10 is 6 plus 10, which is 16. Square root of 16 is 4. It doesn't have to be a nice square number, but I picked a nice square number. Here, -10 is not okay. -10 plus 2 is -8. Square root of -8 is not real. So we really have to have the overlaps. So here is everything less than or equal to 6. And here is everything bigger than or equal to -2. And so then in the middle, right, this is where those two domains overlap, or more mathematically correct, intersect. So the domain of f plus g is everything from -2 to +6. The intersection of the domains of f and g. Now it's a little different for composition of functions, but that's still a similar idea. Yeah, so let's actually look at what happens when we compose these. Actually, I should say, before we compose them, I will just point out that, yeah, so the same thing I just said about needing the overlap of the domain is true whether you add them, subtract them, multiply them, and kind of if you divide them. So what I'm saying here is that f minus g of x, f times g of x, and that's times, this is not a composition symbol, this is a multiplication symbol. Right, this would be square root of x plus 2 minus the square root of 6 minus x. This would be the square root of x plus 2 times the square root of 6 minus x. These both have the same domain of -2 to +6. Because they still both have the same functions that have the same restrictions showing up. Even if some sort of simplification happens later, you still have these domain restrictions. And I'll address that in a minute. But what I will say is that if you divide the functions, so f divided by g, which would be the square root of x plus 2 divided by the square root of x minus 6. There's one value here that's not okay that was okay over there. What is x not allowed to be in this expression that it would have been allowed to be in either of these expressions?
0.
You're on the right track. 0 is still okay. Well, actually, no, 0 is not okay. 0, so, I think I wrote something wrong here, first of all. Let me fix that. So I looked at this and I said 0 is not okay because 0 minus 6 is negative. Sorry, that should be 6 minus x. So 0 is okay here. But what I think you were going towards was that we don't want a 0 in the denominator, which means exactly the people chatting the 6s are exactly correct. We don't want a 6 because 6 minus 6 is 0. Square root of 0 is 0, but division by 0 is not okay. 0 is perfectly fine here, right? 0 times square root of 2 is 0. But here, sorry, 6 was okay here. So yeah, the domain here is almost the same. It's -2 to 6 with the parentheses for the 6 because we don't want to include that 6 in our domain. Okay, so adding, subtracting, multiplying, dividing, pretty straightforward in that you don't lose a whole lot. Or you just get the overlap except for f over g or g over f. So if it was g over f, it would be the same thing except it would be not including the -2 and including the +6. So let's go ahead, sorry. The composition, on the other hand, is going to be a little bit different. So we look at f composed with g, which some people like to write like this. Which I prefer to write like this. That's going to be f of the square root of 6 minus x, which is going to be the square root of, so f is this one, 6 minus x plus 2. So here, I think the way this is written makes it a little more obvious that, oh, of course we have to obey the domain of the inside function, right? We definitely have to have, right here, we need that x is less than or equal to 6. Right, if x was bigger than 6, we'd be taking a square root of a negative. Now, it is also true. Wow, that's not how you write a letter D. And we also need that the total insides are bigger than or equal to 0, which means the square root of 6 minus x is bigger than or equal to -2. So it's still kind of like the other problem, right? We're saying, okay, the thing you're putting into the outer function still has the same restriction, right? Instead of x needing to be bigger than or equal to -2, now we have g of x needing to be bigger than or equal to -2, right? Before, right, f of x equal to square root of x plus 2, we had x bigger than or equal to -2. Now for f of g of x, which is the square root of g of x plus 2, we need g of x to be bigger than or equal to -2. That's what's happening there. Now, in this case, it doesn't really change anything because the square root always gives us a positive result. So there's no issue here. This checks out immediately. So for f of g of x, yeah, I'm going to erase this. So for f of g of x, which is equal to that, the domain is that x is less than or equal to 6. And again, I will point out we always at least have to obey the domain of the inner function in a composition of functions. Okay, let's do the reverse composition and see if there's anything different. So g of f of x. So again, g of f of x is the square root of x plus 2. So already we know for sure that x is going to have to be bigger than or equal to -2, right? Automatically, right off the bat. And then g of x is the square root of 6 minus x, so g of this is going to be the square root of 6 minus so additionally here, so in fact, just like before, right? For the g function, right? For the g function, we needed 6 minus x to be bigger than or equal to 0 or x to be less than or equal to 6. So now for g of f of x, which is going to be the square root of 6 minus f of x, we're going to need f of x to be less than or equal to 6. So we need f of x, which is the square root of x plus 2, to be less than or equal to 6. And this is going to actually add some restriction here. Let me give myself a little more room. So squaring both sides, I get x plus 2 is less than or equal to 36. And then subtracting 2 from both sides, I get x is less than or equal to 34. So here's what I've got. I've got that x has to be bigger than or equal to -2. I also have that x has to be less than or equal to 34. I want the overlap, which is just going to be everything between -2 and 34. So here the domain is everything from -2 inclusive to 34. I think these problems make a little more sense when we talk about the implicit domain or the natural domain, because it's kind of like, well, yeah, of course, if x is bigger than 34, like if x was, I don't know, 38, then this would be 38 plus 2 is 40. Square root of 40 is bigger than 6, and 6 minus a number bigger than 6 is negative. So here it's kind of not as, I think, weird to see that, oh yeah, we are stuck. We have to be bigger than or equal to, or sorry, less than or equal to 34, and still bigger than or equal to -2. Okay.
Can you explain again how you got 6? Negative infinity 6?
Negative 36?
Negative infinity to 6?
Oh, for this previous
Or FG, yeah.
Sure. So for the previous one, right, we have the inside, so the inner function already had a domain of x being less than or equal to 6, which is the same as that. And then what we saw was that when we did the composition, there was no further restriction, right? When I plug in, when I look at this part here, right, this part here needs to be bigger than or equal to -2, because, right, we need square root of 6 minus x plus 2 to be bigger than or equal to 0. So the square root of 6 minus x is bigger than or equal to -2. But that's always true. The square root is always bigger than a negative number because it only spits out positive numbers. So that means there is no other domain restriction. So this is the only domain restriction we have, that x has to be less than or equal to 6. But it can be as negative as you want it to be. All right. What time is it? Okay, got like a half hour left. That's bored. That was the wrong way to go. Sorry. My board gets really tight sometimes. I'm trying to loosen it here a little bit. Come on. Okay, there we go. There we go. Let's see, there was something else that was on my mind. That's not the right notes. Sorry, throwing papers all over the place. Oh yeah, that. So yeah. So a couple of people mentioned that there was some exponential growth stuff or exponential decay. And their problem was similar to, but not exactly like what I'm going to say here. So we purchased an item. Initially worth $8,000. And it loses half its value every 7 years. And I think they just want us to write a model for what its value is. And I think they use like V equals, I feel like someone wrote something like V equals H of T was what I feel like I saw. Does that sound vaguely right? Oops. It's okay if it's not, but I was trying to kind of be similar to what was shown to me. No, I don't see it. Okay, that's fine. I don't know why you would do it like this personally, but whatever. Maybe the H is for half and the V is for value. I don't know. Anyway, we can write a function. And so there's a couple ways to do this. And there's kind of a way that I think some of you might be aware of, and then there's a way I think that your book wants you to do it. So let me talk about the way I think your book probably wants you to do it, or your class probably wants you to do it at this point. And that's that we know that, so here's what we know. We know that H of 0, let's make a table. Why am I trying to be all fancy? Let's make a table. So here's what we know. We have some times and we have some values. We know that at time 0, right when we purchase it, the value is $8,000. And we know that 7 years later, it's going to be worth $4,000. And we know that 7 years later, it's going to be worth half of that, which is $2,000. And we could go on and on, right? We can make this 7 years later, $1,000, and so on. So how do we write a function for this? Well, the numbers we're given here are kind of meant to be somewhat not terrible. Basically, we need a function that starts at $8,000 and then every 7 years multiplies by a half. So I need something like, and this is going to be not quite right, so you might not want to copy this exactly. I want something kind of like H of T equals 8,000 times 1/2 to the T. That's not quite right, because I'm not quite getting the years right, because here, let's see, here H of 0 would be 8,000 times 1/2 to the 0th power is just 1, so it'd be 8,000. And then a 1 year later, I would get 8,000 times 1/2 to the 1, which is going to be 8,000 times a half, which is 4,000. And then another year later, I would get 8,000 times 1/2 squared. 1/2 squared is 1/4. 8,000 times 1/4 is 2,000. So I'm getting the right values on this side, but I'm not getting the right years. Right? My years are off by like a fact. Oh, sorry, that's supposed to be a 2, not a T. Sometimes you say a number and you write a letter because the number starts with that letter. Sorry. So somehow I need to make my years be 7 times as much as they are, right? This is 0 and it's supposed to be 0. This is 1, but I want it to be 7. This is 2, but I want it to be 14. This would be 3, but I want it to be 21. So how do I make the years have to be 7 times bigger? Well, I take this t and what do I do to it? 7t is a very good guess. But let's see. If I plug in t, so now if I plug in t equals 1, I'm going to get 8,000 times 1/2 to the 7 times 1 is 7. 1/2 to the 7th power is 1 over 128. And that looks like it's too small, right? I wanted it to be 4,000. So the problem is, and this is actually kind of a normal phenomenon, right? If you want to make something have to be 7 times larger, we have to divide it by 7 so that the result is that it has to increase to account for being divided by 7. So we actually need here, instead of 7 times t, is we need t divided by 7. Because then, I can put this in here. H of 0 is going to be 8,000 times 1/2 to the 0 divided by 7 is still 0. 1/2 to the 0 is still 1. So H of 0 is still 8,000. And then H of 7 will be 8,000 times 1/2 to the 7 over 7, which is 1. So you get 8,000 times 1/2 to the first, which is 4,000. And H of 14 will be 8,000 times 1/2 to the 14 divided by 7 is 2. Which is going to be 8,000 times 1/4, which is 2,000. So we're getting the right pairing now of inputs and outputs, right? When t is 0, h is 8,000, when t is 7, h is 4,000, when t is 14, h is 2,000, and so on. So that's probably the way they want you to do this problem. There are certainly other ways to tackle exponential growth and decay problems, but I don't think that they're meaning for you to really get that deep into it just yet. So I think I will leave it there and say this is very similar to how I think you should do that problem that a few of you have asked about. Okay. Let's go ahead. There's so many things to talk about. Let me see. Oh, sorry, I had one thing here real quick. Yeah, so I feel like, so I'm going to have this problem, and it is my problem, but it's also your problem a little bit, is that I'm also doing a Co-21A co-class, and a lot of the material in the beginning is very much the same. So it can be hard for me to remember what I've already talked about in one class and not talked about in another class. So I will apologize ahead of time if I'm repeating myself on occasion with types of things, but I think we should do, I really think, yeah, let's do oh no, we definitely did this last time. I remember now, we did do the things last time. So yeah, I was kind of hoping to avoid it because it's kind of a giant pain, but we should probably talk about semi-log and log-log. Graphing. And so I'll say right off the bat, the point of doing a semi-log or a log-log graph is often to make a graph kind of more readable or more meaningful. Let's look at an example. So if I wanted to graph, and I'm probably going to use some Desmos as well. If I wanted to graph y equal to 3 times 5 to the x, with a domain of x greater than or equal to 0. So I want to point out this is an artificial or explicit domain, like we were talking about just moments ago. And it makes sense in this context, and in a lot of contexts, we'll have an artificial domain of x or t being greater than or equal to 0, because it doesn't really make sense to start with a negative time or with a population that has a negative value. So a lot of times you will have an artificial domain of x or t or whatever your input variable is being larger than 0. And so if I start trying to plot some points here, let's see, so x, y. So if x is 0, 3 times 5 to the 0 is 3 times 1, which is 3. If x is 1, I get 3 times 5 to the first, which is 15. If x is 2, I get 3 times 5 squared, which is 20. Sorry, 75. X is 3, I get 3 times 5 to the third, which is 3 times 125. Right? This is getting really big really fast. 5 to the fourth is 625 times 3 is 1875. And so on, right? This grows, I mean, not surprisingly, it grows exponentially. And if I was going to try and graph this, right, it doesn't even if I was using an XY scale where things are the same, right? If my x's are real small, right, y is going to get real big real fast. Right, here's 0, 3. Here's 115, right? I mean, it looks kind of dumb. And we can even see this, right? If we graph this Desmos, I can share it now. I keep clicking the wrong thing. Yep, move. So if I graph this, right? I don't know how to do times. I just realized, how do you do a times in Desmos? We'll figure it out.
You have to click on that little keyboard link on the bottom, and then you can do that.
I think also if you make a space between it, it will also give you what you want. So I'm pretty sure this is the graph I wanted, but yeah, let's see. There we go, yeah. Let's see let's just make sure. I don't want 35, I want.
You can also do an asterisk.
Yeah. Oh yeah, that's right, asterisk. I should have known that. All right, but yes, there is our graph. And if we look at it, right, I mean, it kind of looks like a vertical line because of how steeply it is growing. It's not, right? It definitely is moving to the right and up, but I mean, it's a lot of up for not a lot of right. And so the whole idea is that with a logarithmic graph, you can actually make things more readable. Or I should say, in this case, a semi-log graph. So let me show you what the process is here. And I think there's a way to graph this on Desmos as well, but we will find that in a minute. Sorry. Where'd you go? Sorry, I've got too many tabs open. All right, so here's the idea. This one's actually going to be log. This is going to be log. Somehow. No, somehow. Sorry, we'll clarify in a moment here. So here's what we're going to do. And this is going to be a lot of the time. We're going to take our equation, y equal to 3 times 5 to the x. And we're going to take the log of both sides. And when I say log, I mean log base 10, which is the log we write that doesn't have a base. So I'm going to take log base 10 of this side and log base 10 of this side. And the idea is, and this is going to be true for anything in our class really, most of the time we're looking to make it look like something linear. So I'm trying to make this look like some mx plus b. And I'm going to use my log rules to help me do that. So one of our log rules is that if you have a log of something times something else, you can break that up into 2 logarithms. I can break this up as log of 3 plus log of 5 to the x. The other rule we have for logarithms is that if you have a logarithm of something to a power, that power can come down in front. So this is x times log of 5. So I could write this as, well, yeah, log of y equal to, I'm going to write it as log of 5 times x plus log of 3. And so here's what I've got. I'm gonna change my log of y into a capital Y. That's the semi-log transformation because I'm changing y into log of y, but I'm still leaving x as just x. So this is going to become, we usually use a capital Y when we're replacing a log of y with a y, equals log of 5 times x. So this is our m plus log of 3. This is our b. Now, the hard part is that to graph this, you have to graph it on log, linear, or semi-log paper, which is hard to create on a board. So let me show you a picture of what was done. So here is the graph of this. So you can see that, so on the x-axis is still normal, right? It's still 0, 1, 2, 3, 4, 5 spaced out equally. But the y-axis is not normal, it's logarithmic. So you have 1, 2, 3, 4, up to 10. And so basically, the distance between 1 and 10 is the same as the distance between 10 and 100. So 1 to 10, 10 to 100, 100 to 1,000. Every next power of 10 is going to be the same vertical distance away. Which I know is kind of weird. I did, if you look at the, sorry, that's not what I wanted. If you look in the modules, sorry, it's hard to remember where everything is. If you look at the module for our class, you look down at the bottom, there is some log linear graph paper, which might be helpful. So this one doesn't look quite as extreme, but you can see so log linear and semi-log are the same thing. The x-axis is equally spaced, and the y-axis right here would be 1, 10, 100, 1,000. So each line that's the same distance away is the next power of 10. Sorry, where was I? I lost my spot. Too many spots. Somewhere over here. There we go. So that's what that would look like. So here's the point where x is 0 and y is 3. Here's the point where x is 1 and y is 15, where x is 2 and y is 75, where x is 3 and y is 375. And so we can see that on this log linear paper, you have a linear function, right? Which makes sense. This is definitely linear, right? You've got y equals sum m times x plus sum b. So on the appropriately scaled paper, it's going to look like a linear function. Let's see, what do I want to say? There's definitely more to say here. Let me do one thing here. Sorry, I just want to capture the attendance while I'm remembering to do it. So don't forget later.
So we moved log 5x to the left so it could kind of look like a y equals mx plus b equation.
I mean, really, you don't have to switch the order of these, but yes, I exactly did that so it would look like a y equals mx plus b equation.
Okay.
Yeah, but that is not absolutely necessary. So something to know, which will probably come up, is that when you have an exponential equation where y equals some number times some number to some power that is x, the semi-log graph, so this is a semi-log transformation, also known as log linear, of y equal to sum a times b to the x will be linear. So when you transform this in the way we just did, you end up getting a linear graph when it's a semi-log transformation. But there's also something called a log-log transformation. The good news is you're always going to try and attack these in the same way. Meaning you're always going to attack them by just taking the logarithm of both sides of your equation and then kind of seeing what happens. So let's look at a different example. So this is exponential. So exponential functions are linear when it's a semi-log transformation. And then we also have, let's look at the next one. Let's look at y equals to 5 times x to the 4th. Again, where x is greater than or equal to 0. To be able to do a log transformation like this, you have to have the x is bigger than or equal to 0 because you can't take the log of something that is negative. I guess technically, really, it should be x is strictly greater than 0. Now that I think more about the domain here. 0 should kind of be off limits. I don't know that much. So taking the log of both sides, log of y equal to log of 5x to the 4th. We're going to do the same sort of thing. We're going to use the same rules. We're going to break this up. So we get log of 5 plus log of x to the 4th. And then we're going to bring this down. So we've got log of y equal to, I'm going to rewrite it. So I'm going to write this first. I'm going to write this as 4 times log of x plus log of 5. Okay, so now, unlike last time, right? Last time we had log of y equal to something times just x plus some constant. Now we have a log of y and still a log of x. So both of those are going to get replaced. And we're going to say that this is going to be capital Y. This is going to be capital X. So we've got y equal to 4x plus log of 5. So this is a power function. And it's linear as a log-log transformation. So if we graph this on paper, where both the x and the y-axis were on the logarithmic scale, we would get a linear function. And here's what that would look like. And again, I know this isn't a substitute for doing it yourself. That's a good question, Chris. I'll address that in a second. But here is what it would look like. So we can see, so again, so here you see the x-axis is kind of weirdly stretched out, but it definitely is a logarithmic x-axis and a logarithmic y-axis where 1 to 10, 10 to 100. Yeah, someone didn't quite write these right on this. See that it was written in 100 and 1,000. That should be 10,000 up there. And the x-axis definitely is also logarithmic. So what's happening here again is like you have this straight line because, and that straight line really literally is the line y equals 4x plus log of 5, right? That y-intercept is 5, but it's actually log of 5 when x is equal to, well, when this x is equal to 1, getting it backwards. When this x is 1, which means this x is 0. I know I know this is very confusing when you first see it. I will also kind of, what's the word I'm looking for? Caution you, warn you, or maybe the other side of it. Don't worry too much about this. I think log was something that was, and semi-log stuff was something that was more of a focus in the older textbook. And so people still kind of spend time on it, but I think it's less of a focus in this textbook. So I'm not saying you shouldn't try to understand it, because it is definitely something that we do talk about, but it's not as huge of a focus as it was in a previous textbook. So then something we can do with this is look at some data and then ask kind of, did it come from an exponential function or a power function? So we're kind of short on time. Let's talk through this example as opposed to me writing it for you on the board. Maybe I should do more of that. I don't know. It feels very weird to not write things on the board and just say things at you. But depending on what we see, that might end up being a more, excuse me, maybe I'll just die, a more effective way to do things. So let's look at this question. So this data is, we're being told that this data is either coming from an exponential or a power function, and they want us to find the function that it's coming from. So we're given x values, they're evenly spaced apart, right? 2, 4, 6, 8, 10, 12. We're given y values that are not evenly spaced apart, right? 0.08, 0.12, 0.18, 0.26, etc. So because we know the data comes from an exponential or a power function, right? Here's a power function. It's linear if it's log. Here's an exponential function. It's linear if it's semi-log. So we can use the knowledge to say, well, we know it's either going to be linear if it's semi-log or log. So let's take the logs of the y values and see if that makes it linear. So if we take the logs of each of these values, you can literally get out your calculator and be like, okay, I'm going to do log of 0.08 and get approximately negative 1.10. And log of 0.12 is about -92, and so on. And we see that in each of these cases, right, after we take the logs of the y's, now the logs of the y's are all kind of equally spaced out as well. So that between these 2 points, the slope is negative 0.92 minus 1.10 over 4 minus 2, which is 0.09. And between these 2 points, the slope is also 0.09. And between any 2 points, the slope would be 0.09. Well, if the slope is the same between any 2 points on the graph, that means you have a line. And so by just taking the log of y, we see that, oh, we're getting a line. So that means that we're getting something like this, where we can say, oh, well, we don't have y equals mx plus b, but we do have log of y equals mx plus b, where the slope is 0.09. And the b we still have to find. So how do we find b? Well, the way we usually find b is by just picking a point and plugging it in. So we're going to pick x equal, the first point, x equal to 2, and log of y equal to negative 1.10. So plugging those values in, we do a little algebra, and we solve for b, we get negative 1.28. So then, going a little further, there's the equation, but we want actually the original equation it came from. So to undo it, and this actually I will show you because I think this is worth talking about, because that's we're jumping kind of straight to the end here. If I know that, stop sharing. I know we're out of time. Let me just say this last thing. We can definitely talk more about semi-log and log on Thursday if you guys want to. I just don't know how much time you really want me to dedicate to it. So just the last thing I want to say here. So if this is our equation, log of y equal to 0.09x minus 1.28, I know that I should be able to write this as an exponential equation because it's semi-log, or a power equation. Either way, I'm trying to solve for y. And the way I'm going to do that is by raising both sides as powers of 10. So I'm going to write this as 10 to the log of y equal to 10 to the all this. The left side just becomes y. That's why we did it. The right side you could leave as this, but it doesn't really look nice. We should do a couple things. First of all, we should break this up as 10 to the 0.09x times 10 to the negative 1.28. And then we typically write it as this could be 10 to the 0.09 to the x times 10 to the negative 1.28. This is a more typical way of writing it because now it looks like we have some sort of, you know, b to the x times a. So that's that is something people often do to make this look a little more normal. If we simplify these, right, this approximately is going to be y equal to, this number here is about 0.052 times this 10 to the 0.09 is about 1.23 to the x. So now it looks more like your typical kind of exponential function. So that's what we often do with these to make them look like what we expect them to look like.